record this. Are there any homework problems? Junhao, welcome here today. Any questions on any of the material from chapter 1? I want to go through a couple more topics in chapter 1, and then if we have time, we'll head into chapter 2. Okay. All right. So let's spend a little bit of time working on interconverting compound SI units. So this can be a little bit challenging. Because this type of problem involves more than one step. So here's an example type problem. What they do is they give you a measurement. So remember, a measurement has a numerical value. And that's really, in a sense, that's the difference between a measurement and an observation. An observation can be numerical, but a measurement has to be numerical. So I could say that the sky is blue. That's an observation. That's an experimental observation. But to make it a measurement, we would have to have some associated value, like it absorbs light with at a maximum wavelength of 450 nanometers. That would be a measurement when you assign a number to it. So in this particular example, they have 3 units here. And then they want you to put it in new units. So they want you to put it in grams per mole liter. Okay. Now, this particular set of units, don't worry about them in particular. They don't refer, this set doesn't really refer to anything in particular. It's mass. You might want to be able to recognize that you've got mass units here because of the grams. And then these are moles. We'll talk more about moles when we get to chapter 3. And then this is a volume unit. So it's really, in a sense, there's density in there, right? You got mass over volume, which is density, but you've also have these mole units in there. So what they want you to do is they want you, if you take a look, they want you to convert the kilograms, which is in the numerator, into grams, which is in the numerator. The moles are the same, so there's no conversion there, but they want you to convert deciliters into liters, okay? So what I'm gonna do is I'm going to write out a couple of conversion factors. So let's remind ourselves something about these prefixes. Remember, we had the ones that are less than 1. So one of them that's less than 1 is deci, D-E-C-I, and the abbreviation for deci is D, and it really means a tenth. If you wanted to write it in the old style, you would just write 1/10, a tenth, right? But in decimal notation, we would write it as 0.1. So what I'm going to do is I'm going to make the following conversion relation here. I'm going to say that 1 deci, so we have deciliters here. So 1 deciliter is 0.1 liters. Okay, right? So all I'm doing is I'm saying deci is 0.1. So deciliter is 0.1 liters, and that's your conversion factor. Now, sometimes what you'll see is that when you look these things up, they will do it the reverse way. They'll say that 10 deciliters is equal to 1 liter, which is true. That's perfectly fine. It's just an issue of whether 12 inches is a foot or is a foot 0.08, I'm sorry, is an inch 0.08 feet. So they're just writing it the other way. But I prefer this way because there's a little more purity to it, right? What you're doing is you're using the direct definition of what deci is and putting it as a numerical value there. So that's a perfectly fine way to do it. And then the other one is the kilograms to grams. So same thing, remember kilo is one of the prefixes. It has an abbreviation of K. And written in decimal notation, it's 1,000. Written in exponential notation is 10 to the 3, right? Because 1,000 is 10 times 10 times 10, which is 10 to the 3. So if we're going to do a kilogram, 1 kilogram would be 1,000 grams. 1,000 grams. 1 times 1,000 if you want to write it that way, but It's 1,000. Okay, so those are 2 conversion factors. So now what I'm going to do is I'm just going to do them sequentially, one and then the other. It doesn't matter which one you do first. It doesn't matter which one you do second. We're just going to do them. I'm going to pick one. I'm going to do the one that I think is easier, which is, in general, for me anyways, the numerator is easier than the denominator, but it's not a big difference. So what I'm going to do is take the 0.00759 kilograms per mole deciliter. And I put a little dot here just to indicate that those 2 units are times each other. The dot means times. And then we're going to convert this to grams, right? We want grams. So I'm going to put our 1,000 grams here. And then we're going to put this one on the bottom in the denominator, 1 kilogram. And if you take a look at what happens, the kilograms cancel, right? Your kilograms are now gone, and you now have replaced them with the new unit, which is grams. So, this one you don't need a calculator for. I mean, that is really the advantage of SI units in the metric system, is that often you don't need a calculator to do the conversions because you're just multiplying or dividing by powers of 10. So if you multiply this by 1,000, you just need to move this over 3 places. So you've got 7.59. And now it's going to be in grams per mole deciliter. Okay, so take a look at what I did. I took our definition of the kilogram based on the gram, and then I just used this. This is called dimensional analysis, by the way. They have other names for it, but dimensional analysis is the typical name for it. Okay. So 7.59 grams per mole deciliter, but now we got to do the deciliter conversion, deciliters to liters. A liter is 10 deciliters. So let's come back to this one. So now we want, the logic of this is you look at which one you want to get rid of. You want to get rid of the deciliter, right? Because we want it to be in liters. So that means that in your conversion factor, the deciliter has to be on the opposite side of the division relative to where it starts off at. So if the deciliter is on the bottom to start off with, you're going to have to put the deciliter on the top for them to cancel, right? The logic is if you can get deciliter over deciliter, that's equal to 1. So you've, quote, canceled it, right? So I'm going to put the deciliter up at the top. And then you can put your 0.1 liters at the bottom, right? And then just check, does it actually work? Deciliter over deciliter. Okay, so we're not changing anything here. We're using that. It's just which one we put in the top in the numerator and which one we put in the bottom, the denominator. If you divide something by 0.1, that's like multiplying by 10. So it's going to go up to 75.9. And now you have new units, which is grams over mole liters. Okay, again, don't worry about what these units mean. This is not, I don't think it's actually a set of units that typically go together, at least not all 3 of them. Okay, so different number now, right? So now we have a different number, 75.9. But the reason it's different is because it's in different inches. So for example, in different units. For example, if we measured the distance between New York and Los Angeles, the distance in inches would be a different number than the distance in feet, or the distance in miles, for example, or kilometers for that matter, right? So it's going to have different value, but it actually is, it's the same information. So often what we do is we pick the units so that the numbers are numbers we sort of like. So like often people don't want to report, like you generally don't hear how far is it to the nearest star in miles or kilometers because the number's so big. So instead we use a different unit. We use what's called the light year. And the light year, even though it's got years in it, which you would think that means time, a light year is the distance that light can travel in 1 year. So if something is 4 light years away, that means that it takes light 4 years to travel that distance. So we use the units of light years to refer to, interstellar distances because it's easier to say. It's easier to say something is 4 light years than it is to say it's 10 to the 10 to the 14th miles or 10 to the 15th miles, right? That's just too big of a number. So this, I could see people actually doing this conversion, because now you can say, oh, the answer is 75.9 as opposed to 0.00759. Okay. Let's try another example. Okay. Okay, this one is a little different, Okay, so this one is, you got 3.3 times 10 to the 6th, and you've got grams times centimeters squared over seconds squared. And they want to have that in some number of kilogram times meters squared divided by seconds squared. Okay. So same idea. The reason they call this compound conversion is because there's more than one unit in it. You're having to convert a couple of units here. So one of them is pretty similar, right? In this case, we're not going from kilograms to grams, we're going grams to kilograms, but that's the same conversion, right? So 1 kilogram, that's over here, we're converting it from grams, is equal. Now kilo's 1,000, right? So 1,000 grams. And then we have this other one, which is centimeters squared. Now that's a little more involved, and here's why. Centi is a lowercase c. Okay, all the ones that are less than 1 are lowercase. All the ones that are greater than 1 are uppercase, with the exception of kilo. Just for historical reasons, kilo is a small k. All right. So centi is 0.01. So I'm going to write this as 0.01. Oops, 0.1. Deci is 0.1, centi is 0.01. Centi for, like a century is 100 years. Okay, a decade is 10 years, a century is 100 years. So now we're going to go from centimeters to meters, but be careful, because we're going from centimeters squared to meters squared. So not just centimeters to meters, but centimeters squared to meters squared. So we're going to be a little careful there. So let's do it this way. 1 centimeter is 0.01 meters, right? Because centi is 0.01. So I just put the 0.01 in for centi. So 1 centimeter is 0.01 meters. But we want to square it. That's all that's saying is we want to square it. So what do? We square both sides, right? That's an algebra rule. If you square one side and you square the other side, it's still an equation. It's still an equality, right? So we're going to square both sides. Now it's just an issue of notation. What's the notation look like when you do these things? In general, when you square a measurement, which has number and units, you actually go through the arithmetic of squaring the number. Okay, so you say, okay, well, what is 1 squared? 1 squared is 1 times 1, so that's just 1. Then what we do is, since you can't take a letter and then square it and have it be a different letter, we wouldn't want it to be that kind of system. What we do, I guess you could do that. What you do is you just write the square next to it. So you write 1 centimeter squared. So you just write the 2 next to the centimeter. Now, in a way, that's a little confusing, because if you remember the rules of algebra, if we write it that way, it kind of, you might infer that it just means squaring the meters and not the centi. But our convention, our notation is that the whole unit is squared. So it's not just squaring the meter, it's squaring the whole centimeter, okay? And then you do the same thing on the right side. You square the number arithmetically, so 0.01 times 0.01. Now that ends up being a pretty small number. So I'm going to write it in exponential notation, 10 to the minus 4, right? 0.0001, which is 10 to the minus 4. And then we square the units, so meters squared. Okay. All right, so now we've got that conversion. So that's the extra step with that example. And if that's an area unit. When you see meters squared or centimeters squared, that's an area unit. So often we measure the sizes of properties in area units, right? You would say, hey, how big is that house? It's 5,000 square feet, right? Square feet or square meters. That's because it's an area. To know the size of it, you measure the area. Now, in fact, the size of a house is not its area. It's its volume. That should be a volume unit, which is meters cubed or feet cubed. But generally, we don't do that. It's usually done in area. So now we have our two conversion factors. We have this one, and then we have this one. Okay. So again, it doesn't matter which order you do it in. You can do either one, but just do, one and then do the other. If you're really good at this, if you get practiced at it, you can do them at the same time. So I'm going to rewrite this number. Okay. So let's do, let's do the first one, which is grams to kilograms, right? We want to go grams to kilograms. So the one you want, so what I'll do is I'll put the kilogram up here. And then the goal here, or the strategy that you're using, the tactic, is the one you want to get rid of, you put it on the opposite side of the division sign. So grams is in the numerator, so you want to put your grams in the denominator. And then you just check yourself, right? It's a little tedious when you're learning how to do this, but it's a cool system. And then what it does is it allows you to do more advanced problems that you don't have any idea really, like, you wouldn't have any intuition in terms of how to do the conversion, but this system allows you to do it almost not mindlessly, but it allows you to do it mechanically. And then over time, you get the intuition to what you're doing. So we're going to divide it by 1,000. When you take 10 to the 6 and you divide it by 1,000, that's going to knock the 6 down 3. So 6 will go down to 3. So now you'll have 3.3 times 10 to the 3, right? Because you're dividing 10 to the 6 divided by 10 to the 3. And then now we're going to have kilograms times centimeter squared over second squared. Okay, so now we've knocked it down to 3.3 times 10 to the 3, which is 3,300, which is a smaller number. It's getting closer to 1, right? Again, we generally want to have numbers that are closer to 1 than larger than 1. Okay, so we've done that. So there's a logic to why they want you to do this particular conversion. The second one was the centimeters squared to the meters squared. Once you've got this set up here, it will work it'll work perfectly fine. So what I'm going to do is I'm going to take our intermediate answer. And now let's do the centimeters squared to meters squared. So we have centimeters squared. We want to convert it to meters squared. So that means we need to have those centimeters squared at the bottom. All right, so you put that one down there. And there you go. So that will work, right? The units work out. A nice thing about dimensional analysis is that if you do the dimensional analysis correct, that analysis in the right way, generally you get the right answer. So it's kind of cool. It's not perfect, but it works pretty well. So we're going to multiply that by 10 to the minus 4. So I'm going to go over the exponents in a minute, but essentially what you're doing here, actually, let me show you right here. You've got 10 to the 3, and you're multiplying it by 10 to the minus 4. So one of the nice rules of powers of 10, or any powers of 2, even if you want to do it that way, is that if you multiply numbers together and they have the same base, remember this is called the base. 10 is the base, is a base 10 number, each of them. If the base is the same and you're multiplying them together, you just add the exponents. You just add the exponent. That's really cool. If you're dividing, you subtract the denominator exponent from the numerator. But if you're multiplying, you just add the exponents. So 3 plus -4 is -1. Okay, so what that does is that allows me now to do this in my head, right? I don't have to write it down or put a calculator in there. So 10 to the 3, so times 10 to the minus 1. And that's a perfectly fine way to represent the answer. And now you would have meters squared divided by, oh, I'm sorry, there's a kilogram in there, right? Or a gram in there. Kilogram. And now we'd have meters squared over seconds squared. That actually is a unit. That is actually a pretty good unit conversion problem right there, because it turns out that a kilogram meters squared per second squared, that's actually a real unit, and it's called a joule. And the abbreviation for a joule is J. It's a unit of energy. It's actually the base unit of energy. And energy is typically represented in terms of joules. So kilogram meters squared per second squared is today, these days, preferred over gram centimeters squared per second squared. That's an old unit. People used to use this a lot, but now we use this one here. Sorry, and you don't have to put it in joules. That's something we'll cover in Chem 11. But that would be our answer right there. Okay, 3.3 times 10 to the minus 1 kilogram meter. Remember, the dot here just means times. So 1 unit times another unit divided by another unit. That's a compound unit, right? It's got 3 different units in it, and a couple of them are even squared. So that's pretty cool. All right. Let me see here. All right, let me show you one. I'm just going to show you one example of this. This is called setting up a 1-step unit conversion. Okay, setting up a 1-step unit conversion. So it says in the problem, a student sets up the following equation to convert a measurement, and the question mark stands for a number the student is going to calculate. Okay, so in this particular one, they say, hey, you got 0.050 centimeters cubed times, and then they give you a little box, and then equal sign question mark meters cubed. Okay. So this one, in a sense, you know, when I first look at this problem, it's a little confusing because they actually want you to do kind of 2 things. They want you to figure out what goes in this box here to get this over here. Okay. So take a look at it. Essentially, what they want you to do is to figure out what the number is here. Actually, let me come back here. Okay. They want you to figure out what the unit conversion is for this particular step here. So take a look at what happens. You went from centimeter cubed over to meter cubed. Okay. So we want to go from centimeter cubed to meter cubed. So let's go through it. First of all, a centimeter. Remember, centi is 0.01. So that's 0.01 meters, right? Centimeter is 0.01 meters because centi is 0.01. But we want to cube it. So same idea, you just cube both sides. Okay. So when you cube 1 times 1 times 1 is 1. And then, like I said, with the actual units, you just write the unit again and then put the exponent next to it. So centimeter cubed. Okay. And then, but now we got to cube the right side. So now this is 0.01 cubed. So really that's 0.01 times 0.01 times 0.01. So let's go through that. There's different ways to represent this. What you could do is you could do it as a decimal calculation, okay? So you would say, hey, you know, you just take those and multiply them together, and you would get 0.000001, which is a really small number. Once you get down to really small numbers, you're almost obliged to use scientific notation. Once you get below 0.01, you really want to use scientific notation. So let me show you a different way to do it. What I'm going to do is I'm going to represent this in exponential notation or scientific notation. 0.01 is 10 to the minus 2. 0.01 is 10 to the minus 2. 0.01 is 10 to the minus 2. And remember what I just said a few minutes ago, which is that if you're multiplying numbers together that are in this notation, if the base is the same, remember the base is 10, you just add the exponents. So -2 plus -2 plus -2. And I'll put the -2's in parentheses just so that it's not too confusing. When you add the negative numbers, you just add them up and then make the negative and put the negative in there. So that's 10 to the minus 6. Okay? So you can remind yourself things like this. 1 is equal to 10 to the 0. 0.1 is 10 to the minus 1. 0.01 is 10 to the minus 2, and so forth and so on. Okay? So now we have a number here. So this 0.01 cubed would be 10 to the minus 6, and then you cube the unit. Okay, so there's our conversion factor. Okay. So now what do we want to do? We want to put in a conversion factor. So the conversion factor, let me make this a little bit bigger. Is going to be, we want to go from centimeter cubed to meter cubed. So we want the centimeter cubed on the bottom. And then we want the meter cubed on the top. All right. Here's your dimensional analysis. That's going to cancel. And now you're going to have the correct units, right? The units that you have here are going to be units that you're going to have there, right? So the actual number, if you wanted to calculate the actual number, you would take 0.05, 0.050, and you would multiply that by 10 to the minus 6. So how do we do that? Well, I mean, it's actually, you could just write it that way. That's not a very standard notation, but it's actual value. It's okay to write it that way. But typically the way we would deal with that is this. We would take our 0.050 and we would convert that to scientific notation. So what I'm going to do is I'm going to move the decimal point 2 places. Remember, scientific notation, we want a number that's between 1 and 9 times 10 to the x, where x is x is an integer value. Meaning it can't be 3.3 or 6.2. It's got to be 1, 2, 3, 4, 5, 6, 7, 8, or -1, -2, -3. It's got to be an integer value. So the rule of thumb I gave in a few weeks ago, or a couple weeks ago, was lip, right? If you move the decimal point to the left, the exponent becomes positive or more positive, lip. If you move it to the right, it becomes more negative. So since we're moving it to the right, the exponent's going to become more negative. So here's what you do. We're moving it 2 places to the right, so it's going to become more negative by 2. So what do? We make this more negative by 2. So you get 5.0, right? We moved it 2 places. More negative by 2 would be -8. So there's our number over here. So where the question mark would be, if we wanted to write our answer there, it would be 5.0 times 10 to the -8. Okay. So that problem is, even though in a sense it's kind of simple, it actually has some things to think about in terms of numbers, right? The issue that we're dealing with is that in chemistry, we have atoms that are so small and molecules that are so small and viruses that are so small that we often need to use these prefixes, scientific notation to represent those small numbers. So the 10 to the -8, that's a really small number, right? So we need the scientific notation to do that. So we have to not only know how to do prefixes, we also need to be good at dealing with powers of 10, which is the scientific notation. Okay. Let me come over here. Okay, let me show you this one here. Okay, so this is, again, this is a very similar problem. This is setting up a unit re-prefix conversion. Okay, and so with this one, they give you a value. Don't worry about the fact that it's negative. And they put that in parentheses, and then they have time. Remember, the dot means times, a box here, and then that's going to equal some number of units in deciliters. Okay. So with this one, very similar to the one I just did, they want you to figure out what our conversion is going to be. And even though this is a kind of a tedious conversion, it turns out it's kind of a useful one because the conversion between milliliters and deciliters, that's just something that actually people end up having to do. So in the medical field, it is often the case that concentrations are given in, I guess it's grams per deciliter, okay? So for example, if you're measuring someone's glucose levels, I believe that's done in I think it's actually done in milligrams per deciliter. I think that's the units. Chemists generally don't do milligrams per deciliters. We generally do milliliters or liters, but not deciliters, okay? So these kinds of conversions come up a lot. So for this one, we have milliliters, that's our unit there. And then we have deciliters, that's our unit there. So we're going from milliliters to deciliter, but this is tricky. In a way, it's pretty tricky. And here's why. We have two prefixes. We have milli and then we have deci. So we got to do two prefixes. So I cannot tell you there's only one way to do this. There's actually multiple ways to do this, and different people will do them in different ways. And you can kind of Google this type of problem and you'll find different approaches. So I'm just going to show you mine, which is maybe the most tedious approach, but it should work. And so we're going to start off with the milliliter. So I'm going to start off with milliliters. So the way I'll write this is 1 milliliter. Remember, milli is one of the prefixes, 10 to the minus 3. So that's 10 to the minus 3 liters, right? So the prefix milli is 10 to the minus 3, and then the unit liter is L. So we're not changing that, okay? So here's my strategy. What I'm going to do is I'm going to convert it from milliliters to liters first. Then in the second step, I'm going to convert it to deciliters. Now, like I said, you can Google this type of problem, watch it on YouTube, and you'll find that people will show you methods to do it in one step. But I prefer to do it in 2 steps, okay? It's up to you how you want to do it. So let's do this first step. I'm going to convert it to liters. So we've got negative 5.4 times 10 to the 5 milliliters. So I'm going to multiply it by, we want to get rid of the milliliters and we want to convert it to liters. So we're going to put the liters on top. So 10 to the minus 3 liters over a milliliter. And that will get rid of your milliliters. Now, again, the nice thing about the scientific notation is that if you're multiplying powers of 10, all you got to do is add the exponents. So you're still going to have your negative 5.4. You don't affect that. And then 5 and negative 3. Just add those exponents. 5 plus negative 3 is 2. So now you have 2. But now it's in liters. That's a 2. Okay. So now we've got it into liters. And then in the second step, go from liters to deciliters. So here's our conversion factor for that. 1 deciliter, right? D is 0.1. So that's 0.1 liters, 1 deciliter, okay? So now we want to get rid of liters and we want to convert it to deciliters. So I'm going to take our measurement again. And we want to get rid of the leader, right? So if you want to get rid of something, you put it on the opposite side of the division that you're doing here. So the liters is in the numerator. This we want to be in the denominator. And then you put your 1 deciliter here. Okay. So now your liters are gone. So now you have minus 5.4 times 10. And then, okay, 10 to the 2 divided by 0.1. Okay. You can remind yourself that if you're dividing by 0.1, that's like multiplying by 10. If you're dividing by 0.01, that's like multiplying by 100, right? That's why we actually have to have those older names. 10, 100, 1,000, and then if you're dividing by it, it would be tenths, hundredths, thousands, which is kind of hard to say. So what you're doing is you're multiplying by 10, right? Dividing by 0.1 is like multiplying by 10. Well, 10 is the same thing as 10 to the 1. That's what 10 is. 10 is 10 to the 1. So 10 to the 2 times 10 to the 1, you add the exponents. So you get 10 to the 3. So it's really just a 3 here. But now don't forget, we also have our unit, right? This is not a measurement unless it has a unit in here. Okay. Now, that's a lot of work to do a pretty simple conversion, because if you think about it, look what happened to our answer. It just changed from, right, it changed from 10 to the 5 to 10 to the 3. We just changed it by 2. So that's a lot of work to just do that little conversion. But like I said, you can find other methods for doing it, but I think that's actually the most kind of coherent way to do it. I don't know, it's up to you, but there are ways you can use the number line to do it. But I don't want to go over that. Okay. We're trying to kind of stay consistent with what dimensional analysis is. So let me see. That's pretty much all for that section, but I did went through that. Okay. All right, that's good. All right, so lot of conversions in chapter 1 and a lot of discussion about numbers. So this discussion about significant figures, significant digits. And I just wanted to make a point about Alex. One of the things that can be confusing is that they will use 2 terms. One term is significant digits. And then the other term is decimal point. Okay, so for example, suppose the question asks you to report an answer to 3 significant digits. Okay. Really what they're doing is they're telling you that they want the number, the measurement, to have 3 numbers in it, right? So this one has 3 significant digits. If they tell you they want you to have 3, your answer to be 3 decimal point, okay? That's this one right here. Then really what they're saying is they want 3 digits after the decimal point, if that makes sense to you, right? So for example, if I had 1.631, right? This one would have 4 significant digits, right? Because it's got 4 numbers in it, but it would have 3 decimal point. Okay. So that ends up being an issue when you start putting in your answers for certain calculations, particularly on the exams when you do that. So just be careful. Read carefully when they give you the question. If they say they want the answer to, 3 significant digits, then you would report it this way. If they say they want it to 3 decimal points, then you would write it like that. Okay. Just a little thing I noticed that I wanted to mention to you. Okay, so what I'd like to do at this stage is move on, because some of you are moving on to more advanced or more kind of different topics. I want to talk a little bit, kind of get started here, talking about chapter 2. Okay, so chapter 2 is really, it's a cool chapter. We're going to talk about atoms and molecules and even ions. It's cool stuff. So we're kind of getting a little bit now, taking little baby steps. We're getting into the chemistry here, because if you think about it, a lot of chapter 1 is just dealing with numbers. And the reason for that is that chemistry is an empirical science. It's we make measurements. That's how we figure stuff out, is by making measurements. So we need to talk a lot about units and numbers. And the more you work with them, the more kind of natural they'll become to you, and you'll become very good at it. But now we want to talk a little bit about atoms and molecules and such, because that's really the reason we do all these things. Okay. And so let me talk a little bit about this law of constant composition. Now, we talk about the law of constant composition because it's an important discovery historically. The result is very, very simple, but the idea is pretty deep. And it's essentially this idea, which is that if you were to study water coming from a comet, so you send, now they're sending like these little space probes. It's kind of cool. They send these little space probes. It's like 5-year mission, 10-year mission. What they do is they fly way out, and then they get really, really close to like a comet, and then they try to land it just for like maybe just a little second and maybe scoop up a little bit of the surface and then fly back off and then come back to Earth and then drop it off here as a little payload, and then you can study what's on that comet. So it's cool. And so the point of this, of the law of constant composition, is that if you were to study water, okay, you would find that the composition of water is the same anywhere in the universe. It should be, meaning that all of water has this fixed ratio, this constant composition. And that composition is, you can do it in terms of mass, or you can do it in terms of atoms. Let's do it in terms of mass. For water, the composition is, I'm kind of rounding the numbers here. I'm not being real precise about it, but it's essentially 2 grams of hydrogen for every 16 grams of oxygen. Okay, that's the composition of water, that for every 2 grams of hydrogen, you have 16 grams of oxygen. Another way of putting that would be to say you've got 1 gram of hydrogen for every 8 grams of oxygen. Okay, does that make sense? If you have 2 grams of one thing compared to 16 for the other, that would be the same as 1 gram of the first thing for every 8 grams of the other. The ratio is the same. 2 to 16 is the same as 1 to 8. It's the same ratio, okay? And so what we would claim is that if you studied some substance and you found that the ratio was 1 to 8, hydrogen, H for hydrogen, O for oxygen, that's got to be water. Probably can't be anything else, right? There aren't a lot of compounds that are just oxygen and hydrogen. There's only a few. But if it's 1 to 8 or 2 to 16, it's got to be water. And so what that does is it means that if you take some substance and you decompose it into its elements, you can tell what that substance is if you know what those ratios are. So water is, water is 1 to 8 as a mass ratio. Again, I'll use the symbols, hydrogen to oxygen. Now, there is actually a different substance that just has hydrogen and oxygen. You're familiar with it. You've used it most likely at some point. There's another substance which is 1 to 16, interestingly enough. And that's your mass ratio, meaning how much it weighs, right, of hydrogen to oxygen. So it has a different ratio. It has a ratio of 1 to 16 instead of 1 to 8. This one is water. This one is called hydrogen peroxide. So if you were able to scoop up some material from a comet and study it and find that the amount of hydrogen and the amount of oxygen was 1 to 16, you would then say, no, that's not water. That's got to be something else because water is 1 to 8. Okay, so it's kind of cool. This is called the law of constant composition. It essentially tells us that a substance which we will call a compound. Remember, we said that a compound is a combination of elements. A compound has a constant composition. Meaning, if it's water, the composition is 1 to 8. If it's hydrogen peroxide, the composition is 1 to 16. If that composition is any different, it is not that particular material. Now, the reason that's important is that if you think about baking a cake, if you bake a cake, you could put in, because remember, a cake is made out of elements too, right? Carbon, hydrogen, oxygen, nitrogen, all these elements. So why isn't that a compound? Why is a cake not a compound? A cake is not a compound because I could put in a slightly different amount of oil and it would still be a cake. I could put in a slightly different amount of sugar and it would still be a cake. It might taste a little differently, right? But you can change the ratio. In fact, that's what cooks do, right? They become great by experimenting with how much you put in. You can change the ratios here and there, and it's still fine. It's still a cake. It might even be a better cake. But for a compound, you cannot do that. A compound has what we call a fixed ratio, a constant composition that does not vary anywhere in the universe. Hydrogen to oxygen. So for example, there's this compound, let me show it here. Create a new one here. So this compound is, let me draw a little picture for you. Oops, a little error there. This compound is called glycine. Glycine is an amino acid. It's a building block of proteins. And it has 4 elements in it. It has carbon, it has oxygen, it has hydrogen, and it has nitrogen. So if you were to look at the mass ratio, what you would find is that it's 5 grams of hydrogen for every, let's do the carbon next, 24 grams of carbon, C for carbon. And then for every 14 grams of nitrogen, for every 32 grams of oxygen, okay? So, you know, I could change those numbers and make them 1 to something, but that's fine. And so that's what glycine is. It's a fixed, so any other ratio, meaning if you had 5 grams of hydrogen for every 25 grams of carbon, so it was like 5 to 25, that would not be glycine, that would be something else. So this constant composition, that's what allows us to define and actually experimentally determine what a compound is, okay? So let me show you an example here because some of these problems are a little, I guess the word might be obtuse, they're a little challenging. So again, this is using our law of constant composition. Okay, So what they do in this particular problem is they give you 4 samples. 1, 2, 3, and 4. And then they give you the mass of the first element. E for element. So remember, an element is like hydrogen, carbon, oxygen, nitrogen, these pure substances that we find in nature. We'll talk more about them when we get to the periodic table. So we're only looking at compound that has 2 elements. So we're not worrying about ones that are more complicated than that. So what they do is they tell you the masses. So they've analyzed these substances. And what they find is that for each sample, they get different masses, right? These are different masses. And essentially what they want you to do is to determine whether these substances are the same substance, right? And if they're the same substance, that would mean that they're a compound, right? If you take different masses of this substance and you get the same ratio, if you get the same ratio each time, that means it's a compound. That's essentially what we're determining. So here's how you go about it. You could, what's kind of helpful, remember I was writing these sort of like for water, I said it's 1 gram of hydrogen for every 8 grams of oxygen for water. So what you can do is you can do the same thing here. The way you do that is you divide both of the numbers by the smaller amount. And the reason you do that is if you take the smaller number, which in this case is 5.0 grams of element 1, and you divide it by itself, the smaller one is 5.0, right? You're going to get 1. So if you divide 5 by 5, you get 1. So you have 1 gram of E1. But then you divide the second one by the same number. So you take 17.1 and you divide that by 5, okay? So I'm sorry, let me just pull up my little calculator here. So 17.1 over 5, and you get 3.42. Okay, so that all I'm doing there is I'm dividing them both by the smaller number to have one of them be 1, right? Okay, now let's try the second one. You do the same thing. You divide each of them by the smaller numbers. So 5.4 divided by itself, of course, is 1. So it's 1 gram of E2. And then you do the same thing for the other one. You take your 18.5 and you divide that by 5.4. And take a look, you got the same answer, right? It's 1 to 3.42 grams, okay? So it looks like the ratio is the same. So let's just be careful. Let's try, you know what? I think I just did the third one. I didn't do the second one. Let me do the second one. I'm sorry. Let me, I didn't realize there were 4. So I did that one and then I just did this one. So again, it came out to, there we go. So let's try the second one. So again, yeah, the second one, you got 3.8. So you divide that by itself and then you divide the second one. So the second one is 13.2 over 3.8. And here we get about 3.47. So that's a little different. Okay, so let's try the last one. The last one, 2.7 divided by itself is 1. And now let's do the 9.3 over 2.7. 3.44. Okay, so if you take a look at these, they're a little different, right? They're not exactly the same. Like 2 of them are the same, but 2 of them are a little different. Okay. So what you would do is you would say this. How many digits do we have here? We have 2, we have 2, we have 2, we have 2 digits in there. So if you look at my ratios here I have 3 digits. So what I'm going to do is I'm going to round them to 2 digits. So if you take your 3.42, so I'm doing the first one, and you round it to 2 digits, you would have 1, 2. So you have 3.4. If you do the second one, 3, 4, 7, you round that to 2, you get 3.5. If you take the third one and you round that to 2, you get 3.4. And you take the fourth one, you round that to 2, you get 3.4. So it looks like they're pretty close, right? It's 1 gram of element 1 for every 3.4, 1 gram of element 1, 1 gram of element 1, 1 gram of element 1 for every. This one's a little different. It's a little bit off, but it's pretty close. It looks like they're all about the same. They're all around 3.4. So here would be our conclusion from that. Since the ratio of element 1 to element 2 in different parts of this sample, it always comes out the same, right? That tells us that it must be a compound. And sometimes they call that a pure substance, because a compound is a pure substance. Suppose that we had gotten 1 gram for every 4.5. And then for the second one, we got 1 gram for every 3.4. See how these ratios are different? So imagine again, you're looking in your little cake batter. If you keep pulling out different parts of the sample and you keep getting exactly the same ratio of element 1 to element 2, that means it's a compound. If you get different ratios, meaning a sample from here, it's different than it is over here, that means it's a mixture. So this right here would be a mixture. It's not a compound because the ratio is not always the same. Okay. Let's see. The last step in this particular problem is the following question. If you do believe it is a compound, if it is a pure substance, and they tell you that the entire compound, a new sample, (10 grams). Okay, so that's the whole compound. How much of the compound is element 1? So you can't do that calculation if it's a mixture. So if it's not a pure substance, you can't do that. But if it is a compound, which we determined it is, then you can do that. So here's how you go about it. What you do is you come back to the calculation that you just did. Oops, sorry. Okay, the compound we just did, we found that the ratio is 1 to 3.4. It's 1 gram of element 2 for every 3.4 grams of element 2. Okay, so I'm going to write that down. 1 gram of element 1 for every 3.4 grams of element 2. So here's what I'm going to do. I'm going to say, okay, suppose we put these two elements together. How much would it weigh? Well, that would be 4.4 grams, right? So that's your compound. So now what I'm going to do is I'm going to say this. How much does element 1 weigh out of the total? I'm just making a fraction. Out of the total 4.4 grams, element 1 weighs 1 gram. It's 1 over 4.4. So now if I have 10 grams of the compound, I'm just going to multiply that by 10 grams. And that will tell me how much, if I had 10 of the total, how much of it would be element 1. So you just multiply this by 10. So 1 over 4.4 times 10 is 10 over 4.4. and you would get 2.3 grams. Okay, so here's essentially what you're doing. You're saying, look, if I have a sample that is made up of 1 gram of element 1 and 3.4 grams of element 2, right? That's what we determined in the first part. Our total would be 4.4 grams. Okay, so 1 gram is element 1, the rest of it is element 2. So now I'm saying, what if instead of having 4.4 grams, I now have 10 grams of the compound? Okay, well, that's just going to make this bigger, right? It's going to be bigger. So now you're going to have more than 1 gram of compound 1. You're going to have 2.3. And you're also going to have more of element 2, right? Here you would, I mean, you know, it would be 7.3 grams. But you're going to have more of both. So the way you do that is you say, how much in the first part of element 1 did I have, divided by the total, so 4.4, and then just multiply that by your new total, right? If you multiply that by your new total, that'll give you how much of the first element you have in that different sample. So that's actually the first type of problem in chapter 2, talking about, it's in a sense is sort of a historical problem. Chemists don't generally do calculations quite like that, but it does lead us into some problems that we'll do in chapter 3 as well. So for our next meeting, what I will do is I will talk more about the structures of these atoms and a little bit about the periodic table. And then we'll talk about atomic mass and ions and such like that. We'll get into that over the next few weeks, okay? So reach out to me if you have any questions today or this week. And I hope things are going well for you. I hope getting back into post-spring break isn't too difficult for you. And again, reach out if you have any questions. Take care.
Professor?
Yes.
Sorry, can I just ask, I was just confused